Thank you. Hi everyone. Today I'll be talking about my work on simplicity and optimality in mechanism design beyond the single parameter regime. I will mostly be focusing on my work in revenue maximization for multi-item auctions. But towards the end, I'll briefly discuss some recent work on welfare maximization in the rich advertising auction setting. But yeah, so this is joint work with Pravesh Kotari, R.L. Schwartzman, Sahil Singla, and Matt Weinberg. Okay, so I'll just jump right in and state our results, and then I'll provide more context for this soon. We have a revenue maximizing seller with n items and a single unit demand buyer with independent values for each item. Don't worry if you don't understand any of these terms. I'll explain what they are and like why we care about them in a second, but this is our setting. And we show that you can get a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time. Okay, so in n to the log n time, we can get almost optimal revenue for this setting. So revenue maximization is a very common goal in like many different settings with various practical applications. But let us start with the very simple setting of selling a single item. I'm sure a lot of you are very familiar with this, but I want to quickly go over it just to make sure everybody is on the same page. We have a seller with a single item, a soccer ball, facing a single buyer, and the seller's objective is to maximize revenue. He doesn't have any intrinsic value for the item. All he wants to do is to sell it and make as much money possible. So purely as an algorithmic problem, this is clearly trivial because if you know how much the buyer is willing to pay, just sell the item at that price. Okay, if you know the max value that the buyer is willing to pay, just sell the item at that price. But clearly a strategic buyer has an incentive to lie and say that her value is 0. So now what do we do? And this is why it is very important to design mechanisms that are like algorithms that are robust to strategic behavior so that we can get good performance guarantees despite strategic agents. Okay, and one way to formally model this problem is to say that the buyer's value is being randomly drawn from this known distribution F. So think of it as the seller like knows the population F from which the buyer arrives, like a random buyer arrives from this population F, and he knows how the population in general values the soccer ball, but does not know the exact value of this particular buyer he faces. And the question is, can we design mechanisms that will incentivize the buyer to report truthfully, okay, to not lie about her value? And our goal is to find like the optimal truthful mechanism. Okay, so yeah, this is clearly the very famous like Meyerson instance. So we have an input which is just a distribution F, and we want to output the truthful mechanism M. And by mechanism here, I mean that given a value, it maps it to some like allocation and price pair, and the allocations can be even randomized. And the utility of the buyer for an allocation and price is just going to be the value from the allocation minus the price, V times A minus P. And by truthful, we mean that the utility of the buyer for reporting her value truthfully is better than, like, is at least as much as reporting any other value V prime. Okay, and our objective is to maximize revenue, which is the expected price paid by the buyer. Yeah, so in the 80s, Meyerson like solved this problem very elegantly and even got Nobel Prize for this. He showed that you can get a simple mechanism that gets the optimal revenue in this setting. He showed that all you have to do is to post a single take it or leave it price P star. That is, the buyer will pay price P star and take the item, or pay nothing and get nothing. Okay. Note that in mechanisms with just like a fixed price P, the item sells only when the value of the buyer is greater than P, right? So only then she will get non-negative utility. So the revenue from such a mechanism is just P times the probability of sale, which is P times the probability that the value is greater than P. Okay, and P star is exactly the price that maximizes this expected revenue. And Meyerson showed that this is the optimal thing to do in the single item case. Like, you don't need any randomizations or whatever. All you need to do is to post a single deterministic option, and that is like that will get optimal revenue. Okay, and we are interested in selling multiple items. So what happens in the 2-item setting? Unlike the single item case, here Daskalakis et al. Showed that the optimal mechanisms here can be randomized and can even have uncountably many number of options, right? So, and this is true even when the item values are drawn independently. That is, the buyer's value for the soccer ball is independent of the buyer's value for the baseball. And here the value for both the items is just the sum. So why am I talking about like independent values suddenly? It's because in the correlated case, things are even more crazy. Hart and Nissan showed that here, not only do the optimal mechanisms have infinite many options and give infinite revenue, any simple mechanism can have, like any finite mechanism can only get finite revenue. Okay, so they show that there is this infinite gap between what is optimal and like what any simple mechanism can achieve. Okay, so we really can't say much about the correlated setting, and so it's very important to like understand and resolve the independent setting. And in this talk, like for this major part of the talk, I will only be talking about independent values. Okay, so yeah, so the question is, in the 2-item setting, can we get a simple mechanism when the buyer's values are drawn independently for each item, right? And more generally, in the n-item case, can we get a simple mechanism that gets good revenue when the buyer's values are drawn independently for each item? Okay, and this is exactly the setting that we tackle, but I still need to explain to you one more term, which is unit demand. So recall that so far I've just been saying that the buyer's value for each single item is drawn independently. I still haven't told you how a buyer values like different sets of items, right? And many different valuations have been studied in the past, out of which I would say unit demand and additive are like 2 of the more popular ones. A unit demand buyer only cares about a single item. So her value for a set of items is just the max single value, like a max individual value of the items in the set. Okay, so it's as if you just gave her the favorite item in the set of items like that you allocated. And additive buyer, on the other hand, is happy with however many items that you give her, and her value for a set of items is the sum of the values of the items in the set. Okay, so throughout this talk, I'm just going to be focusing on the unit demand setting, but the additive buyer setting is like very well studied, and I have some results about them that I will briefly discuss, but I'm not going to be getting into too much detail about it, but you can ask me about them if you're interested later. Okay, so yeah, we have a unit demand buyer, and like I hope the setting is now clear. Okay, so this is our setting. Again, we have a seller with n items and a unit demand buyer whose value for each item is drawn independently. And the question is, can we get simple mechanisms that give good revenue? Right? Is the setting clear for everybody? Okay. And we study simplicity formally through the lens of computation. So consider this computational problem where we are given as input n independent distributions, f1 through fn, and we want to output a truthful mechanism m. Okay, and the objective again is to maximize revenue, the expected price paid. So can we do this in a computationally efficient way? The question is, can we find the optimal truthful mechanism in polynomial time? Okay. So let's try to do this. Let's try to solve a simple instance with a very naive approach. We just have a buyer.
Divya?
Yeah.
What do you assume about the access to the distributions?
Good question. So I am going to assume that the access to the distribution is going to be like an oracle. So by the input size, we only talk about like n items. We are not going to take the support of the distribution into account. We want something polynomial in n. So I'm going to think of the distribution as like we have oracle access to like the PDF and the CDF, and more importantly, we need to be able to compute the Meyerson price of a single distribution of F1 or like of any Fi. We need to be able to compute Meyerson prices through an oracle access. That is what I'm going to assume, because I'm going to assume that Meyerson is going to be simple for single agent, single agent and like single item, and that is going to be the assumption I have. Like you have oracle access that tells you what is the Meyerson price. Like if you give any threshold t, it will tell you what is the Meyerson price about t. Like if you can only sell at price about t, what is the Meyerson price? Okay.
And if you can, and if you only know epsilon Meyerson price, is that enough? Because computing the precise Meyerson price may be a very difficult problem. But within epsilon may be much easier. Would this suffice? And you'll get maybe 2 epsilon approximation or whatever, I don't know.
So yeah, I think it should be fine, because it will give, we will see that like the way we will prove like truthfulness and stuff will be like going from epsilon truthful to truthful mechanisms. So I believe it would be enough, but we don't even think about computing the, we don't even count calculating the Meyerson price as a computational cost. We just say that we have oracle access to it. Like that is how we view the problem. But yeah, I think it should be fine. I think if you have epsilon like access to the Meyerson price, it should be fine. Yeah. Cool. So yeah, so we want to find the optimal truthful mechanism in polynomial time, and let's try to solve this for a very, very simple instance. The buyer's value for each item is just going to be 1 or 2 uniformly at random. And we can actually solve this very directly through a linear program. So for each buyer type V in the distribution, I'm going to have variables for all item allocations and price. That is, Xij is the probability that item J is allocated, and the price P that you need to pay for this allocation vector. And the objective is to maximize revenue, which is the expected price paid, and we will have to satisfy certain constraints while calculating this. So first is just the unit demand constraint, which just says that the allocations are a lottery about which item you're going to get. So the probability sum up to 1. And the second is an incentive compatible or truthfulness constraint, which says that the utility of reporting your value like truthfully is better than saying any other value V prime. And the third is the individual rational constraint, which is just a special truthfulness constraint, which says that reporting truthfully is better than not participating. That is, you always get non-negative utility. Okay. Is that clear? Okay. And the main thing to remember is that this exactly solves the revenue maximization problem, but this is already exponential in n, even for the simple instance. Even for the simple instance where the support size is 2, this linear program takes exponential time, because there are exponentially many variables and constraints that we need to take care of.
Divya?
Okay. Yeah.
Divya, can you explain again why the unit demand allocation? I mean, the unit demand, the seller can allocate more than one good, right?
But
he might not. Yeah, sorry, go ahead.
Yeah. It's just going to be without loss of generality for the unit demand buyer. Like, because we are looking at the unit demand setting, this makes sense. And it's going to be without loss of generality, and it helps making it a linear constraint here.
So this for me at least, this is not intuitive, right? Because in a unit, for example, I can allocate the whole bundle, the blank coalition, and I don't know why the buyer bought it for $2. He bought it for $2. I have no one. I don't know which is the item he likes. And
I completely agree. I agree, but like,
so I'm not sure why this is without loss of generality. Can you convince me?
There is always a solution, Ran. There is always a solution. I mean, if there is a solution where you allocate more than one good to one person, well, whatever the excess give to somebody else, that can only increase the revenue. So there is always a solution that satisfies this constraint. It may not be the only one, but there is one like.
It's just without loss of generality that like you can turn any mechanism that you're describing by into a mechanism that always gives something at most one. Because for example, in the case of giving the whole bundle, like giving every item with probability 1, like the whole bundle at some price 2, is literally same as like splitting this up into like n different options, and you're asking them to take the option that they take the item that they value more. So
I see. Okay.
So it's still like totally equivalent.
Thank you.
Yeah. Right. Okay.
And like somebody says J equals I, just to, if you are trying to read the formula. Somebody said it in chat.
Forgetting to change this slide. Thank you for noticing that. Yes. Wherever I say J, I actually mean I here. Like there is only like there's one buyer and we have n items. Okay. So yeah. Thanks for catching that. Yeah.
Somebody is Amos, yes, by the way.
I see. Okay. Yeah, everything is like sum over J, sum over I, whatever. Like J and I are the same here. Okay, thank you. My bad. Cool. So yeah, this is going to be exponential in n, and like, can we do better? The question is, can we find a polytime solution? Is this polynomially solvable? And unfortunately, the answer is no. This is a computationally hard problem. Shen et al. Showed that even when the support size of each marginal is 3, that is like the items values can take at most 3 different values, you cannot find the optimal mechanism in polynomial time unless the whole polynomial hierarchy collapses. It is a computationally hard problem to find the optimal mechanism. Okay, but all is not lost. Like, what do we do when we are faced with
sorry, question. You vary the number of goods and the number of people, both, only one of them. In what you get this hardness?
Sergio, the number of people is 1.
Yeah, like it's a
so
single buyer.
It's just the number of items.
Oh, sorry, there is just one buyer. Oh, I see. Okay, that answers my question. Sorry, I thought there are also multiple buyers, but sorry, my mistake.
No. We are in the single
one buyer, but multiple goods. So the variable is the number of goods.
Exactly.
That's it.
Exactly.
Okay.
Yeah. So like when I say polynomial time, I mean polynomial time in n. Like n is the number of goods. That's it. And we only have a single buyer. Yeah. Cool. So
and what is pH for non-computer science people?
It's just the polynomial hierarchy collapses, which is, I guess, in this case,
means P equals NP. That's
no, it's
for me, or it's much.
It's more than that. It's not just P is equal to NP. Like it can be like
okay. You know what I mean. Everybody else knows. I mean, I don't. Go on.
It's like it's not just P is equal to NP. So P is equal to NP is like a decision problem, right? So this is actually going to say something like this is it's not polynomially. It's not going to be solved polynomially. Like the counting problem is not going to be solved polynomially. So there is this polynomial hierarchy that kind of talks about like the oracle accesses you have. Like, what is it polynomially solvable if I have polynomial access to an oracle, like things like that. So there is this whole like chain of things, and this thing will collapse. Like it will say that everything is equivalent to P. It's not just P is equal to NP, but it is not important. It is, all you need to know is that it is computationally hard to like find the optimal mechanism. Yeah.
I mean, is this again the conjecture being that this is as hard as P as
it's harder than P is equal to NP. Like
so even if P equals NP, you could still have this being hard problem.
Yeah.
That's what you are saying.
That is my understanding of complexity.
Okay.
Yeah.
So
Okay.
I guess the question is to what it collapses. Usually when we say the polynomial hierarchy collapses, it's usually not to the level of P, and then it's not equivalent to P. I mean,
no,
but
so it actually collapses to P. I'm saying that like everything collapses to P, not just NP is collapsing to P.
Usually when people say the polynomial hierarchy collapses, I don't know what's in the specific result that you cite here. Usually they mean it collapses to the second level or something like that. And then, but I didn't see the detail of the paper. But anyway, it's a complexity assumption that, I mean, if you manage to collapse the hierarchy, I mean, it's almost as good as proving P equals to NP. Not as good.
I think if I also don't remember the exact result, but I think it collapses all the way to like P, like, but it's difficult when P is equal to NP.
But
That
then
is,
they just say P equals NP, but never mind. Okay.
okay. I see. Okay, yeah. So this is a computationally hard problem to find the optimal mechanism. Okay, and but there is no worries. Like, what do we do as computer scientists? We approximate whenever we find a hard problem. And it turns out like there's a line of work by Chawla and et al. Which establishes a 1/4 approximation to the optimal revenue in polynomial time. Okay, so you can get 25% of the revenue with a simple mechanism that like, and you can find it in polynomial time. But is 25% of the revenue really good enough? Can we do better? Can we get better than a 1/4 approximation? Until now, we did not know anything better than a 1/4 approximation. We didn't even know a 1/4 plus epsilon approximation for like this general problem. And our work tackles this question exactly, and we answer affirmatively that yes, we can do better, and we can do much, much better. We can get all the way to a 1 minus epsilon approximation to the optimal revenue, and we do this in quasi-polynomial time in N. Okay,
wait,
so
can you please go back to the previous slide, because after the 1/4 you cited some other 1 minus epsilon result. For additive.
that is an exponential time. Yeah, and it's for additive. Yeah. Okay, technically you can get a 1 minus epsilon approximation using the same thing for unit demand, but it is going to be exponential. It won't be sub-exponential. Yeah. It was not actually done, but you can like their result actually like will go through if you do like the most obvious thing for the unit demand. It will be exponential in right. Yeah, good catch. Yeah, so we show that you can get a 1 minus epsilon approximation to the optimal revenue, and we do this in quasi-polynomial time. So we can get almost optimal revenue. Yeah.
You mean to the optimal revenue or to the optimal mechanism, which is a much stronger statement? You suddenly changed. You are getting an approximation to the optimal mechanism or to the optimal revenue?
I'm getting to the optimal. I'm just saying that it's a mechanism that gets a 1 minus epsilon approximation to the optimal
revenue. So it's 1 minus epsilon optimal. You are not getting an approximation of the optimal.
No. Yeah. So yeah,
that's a very different. That's a much stronger result.
Yeah. I'm not saying. I mean, what like by that do you mean that anything that you
are within an epsilon neighborhood of the optimal mechanism?
No.
You're saying.
No, it's not that. Yeah.
Okay.
It's just saying that we like
that is 1 minus epsilon optimal.
Yeah, it's
okay.
1 minus epsilon optimal. Yeah, it's 1
we
minus.
We should change the word mechanism to revenue.
Okay. Yeah, I'm just saying that we can get.
What do you even mean by optimal revenue, Sergio? Like is
I mean, a mechanism that gives you 1 minus epsilon of the optimal revenue is called 1 minus epsilon optimal. A mechanism that is within epsilon of an optimal mechanism. Okay, as a mechanism, it's within epsilon. So all the menus, I mean, probabilities and payoffs are within epsilon of the optimal mechanism. That's what I will call a 1 minus epsilon optimal mechanism, or epsilon, whatever. Yes, it's a very different concept.
I understand what you're saying, and I'm sure there are also other ways to define what 1 minus epsilon approximation to the optimal mechanism is. So yeah, I don't mean any of those things. I just mean that you get 1 minus epsilon approximation to the optimal revenue. Like I agree. Like I don't see people doing this to say that like you get everything that is close to like 1 minus epsilon approximation to the optimal mechanism. But yeah, I will change this. It is, you don't.
I think in your previous slides, by the way, it said correctly optimal revenue, not mechanism. That's why this jumped to me.
Yeah. Sorry. Yeah, I literally do mean that you get a 1 minus epsilon approximation to the optimal revenue, and you can find this mechanism in quasi-polynomial time. Like that is what I'm saying. Yeah. And right. So what I'm saying is that we show that you can get a almost optimal revenue in almost polynomial time. Like that is our main result. Okay, for the unit demand buyer setting. Just recall again that like Shen et al. Showed that it is computationally hard to find the optimal mechanism, and Shavla et al. Established a 1/4 approximation to the optimal revenue in polynomial time. And we extend this to a 1 minus epsilon approximation, and we do this in quasi-polynomial time. So we get a QP-TAS. Okay. And our work holds not just for like finite support distributions or anything like that. It holds for any unbounded support distributions as well. Like the only thing we need is that our unit demand buyer has a product distribution. We have independent items. There is no other restrictions on the marginals, and we can get a almost optimal revenue in quasi-polynomial time. And this is the first such like sub-exponential like mechanism that gets almost optimal revenue for a very general class of distributions in this like line of work. Like we didn't know something like this before. Okay, so yeah. Right. And I also want to quickly talk about the additive buyer setting. There is a very similar history here. Daskalakis et al. Showed that even when the support size is 2, the optimal, like finding the optimal mechanism is like computationally hard. And Babayev et al. Showed that you get a simple mechanism that gets a constant fraction of the revenue. They give a 1 minus epsilon approximation to the optimal revenue in polynomial time. And we extend this again to a 1 minus epsilon approximation in quasi-polynomial time. And this result holds for like any like finite distribution marginals. It's not more general than this. It like for any additive buyer with like finite marginal support, we can get the almost optimal revenue with almost polynomial time. Okay. And we also have like other interesting results in like different restricted settings. You can ask me more about them later if you're interested, but I won't be talking about them now. So coming back to our main result for the unit demand buyer, we show that you can get a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time. Okay, and this is true for any product distributions. We don't assume anything about the marginals. Is there any questions about the results, like before I move on? Okay.
Sorry, can you say what quasi-polynomial means?
Yeah, quasi-polynomial means n to the log n. So it's better than exponential. It's better than 2 to the n, but it's higher than any polynomial. So it's n to the log n.
Okay, thanks.
Yeah.
I guess you still assume that the Marsden price is finite, because for unbounded distributions, the Marsden price could be infinite.
Correct.
So it's not any FI. It's not any FI. You still have some restriction.
Right. I mean, if the Meyerson price is infinity, there's nothing really to do, right? You just sell one item at infinity, then basically. But I agree. Like it's not. It is we assume that like you have finite revenue. That yeah. Like all the Meyerson prices are finite. Yeah, I agree. Yeah. Okay, thank you. Okay, so today I'll be like not really like proving our results as such, but I want to like talk about some technical challenges that are there in this setting that like obstructs us from going beyond what is like previously known. Okay, like I want to talk about the technical challenges that we face in like going beyond what is previously known in this setting. And I'll start by talking about a very, very special case of our setting called symmetric distributions. And this was the only case for which we could say something for the setting. Like beyond this, we really didn't know anything at all. And don't worry about the text. Like for the symmetric distribution case, Daskalakis and Weinberg have this very nice result fully like resolving this setting. They show that you can get the optimal mechanism in polynomial time, right? So for this special case of distributions called symmetric distributions, they show that you can get the optimal mechanism in polynomial time. And what do I mean by symmetric distributions? Let's look at this very like a toy instance to get some intuition. Look at a buyer type from a distribution. Let's say her value for the soccer ball is 5 and the value for the basketball is 8. And we have another buyer type with swapped values. Her value for the soccer ball is 8 and her value for the basketball is 5. Okay. So if in our distribution, the probability of seeing these two buyer types is the same. And if it's the same for like any pairs of X and Y, if the probability of seeing such two buyer types is the same, then we say that the distribution is symmetric about swapping the basketball and soccer ball. Okay. So like in general, we say that a distribution D is symmetric with respect to a permutation sigma if for all buyer types V in the distribution, the probability density of V is the same as the probability density of the permuted type sigma V. Okay. And why do we care about this? Why is this interesting? It's because this reduces the problem size a lot by grouping together like equivalent buyer types and treating them similarly. So for instance, consider this very, very highly symmetric example where you have n identical buyers, n identical items, and the value for each item is just going to be 1 or 2 uniformly at random. Again, there are 2 to the n many different types of buyers, and actually this is the same instance that we saw earlier to the naive LP, and we know that you can solve this directly using an exponential size LP, right? Like for the simple instance, we know we can write an LP, but it is still exponential in n because the number of variables and constraints depend on the are exponential. It's going to be 2 to the n because there are 2 to the n many buyer types. Okay, but we note that to capture the buyers, to represent the buyers in our distributions, all we need to know is how many items they value at 1 and how many items they value at 2. That is, I'm going to have a representative RK for all buyer types with exactly k items at value 1 and n minus k items with value 2. Okay, so there will be like n many representatives. And we see that this actually helps in reducing the number of variables from exponential to linear in this new like modified LP. So again, we will have like allocation and price variables, but now we will only have them for the representatives, not for all buyer types. And we again want to maximize the expected revenue. And here we group together, note that we group together like buyer types of the same class, same representative. Okay, and we again do this while like satisfying certain constraints. These 3 are like the same constraints from before. And there's also this additional constraint that makes sure like a representative actually makes sense. Like that, like you won't lie about your representative. Like the main thing to remember is that this actually exactly solves our original revenue maximization problem, but this can be done in polynomial time because there are only like a linear number of variables and like polynomial constraints.
So Divya,
okay. There is one thing you should...
Sorry, go ahead, Sergio.
Go ahead.
Okay, my question is this result robust to approximately symmetric distributions?
Exactly. This is going to be what I'm going to be talking about. Like it was not, I mean, nothing was known like that before. Nobody knew how to like extend this result beyond exact symmetric distributions. And I'm going to tell you more soon about
Great.
like approximately symmetric distributions. Yeah.
But you still, you have to say that if there is a solution which is non-symmetric, because the set of solutions is convex, taking the average is going to give you something that is symmetric with respect to whatever symmetries you've assumed, and that's why it is. It depends only on RK.
Right. Yeah, that's true. Yeah, I did not want to like include too many details about it, but yeah, that's exactly true. Like you can like we're not saying that there only exists a mechanism that is like symmetric for the symmetric distribution, but like you can always make it into a symmetric mechanism. I agree. Like by just taking like convex combinations of everything. Yeah.
So that also says for Michal that there is a symmetric 1 minus epsilon optimal, but you are asking something different. You want a 1 minus epsilon symmetric, which is much more general.
Yeah. Like Michal is asking more about like if your distribution is 1 minus epsilon approximate, symmetric, what can you say about it? That is a little bit different, and that is going to be a bit tricky. It will also depend on what we mean by 1 minus epsilon approximations to symmetric distributions and stuff. I'll get to them. I'll talk about them soon. Like we will get to that part. Yeah. So this is actually the spirit of their result. Like I told this for like a very special instance, but like this is the spirit of the Dust-Clarke-Weinberg result. They say that like if you have distributions such that you can partition the items into S different groups, and within each item, everything is identical. Everything is IID. And the support size of the marginals is just going to be at most C. Then you can find the optimal mechanism in time n to the CS. Okay, so if C is a constant and S is a constant, you can get the optimal mechanism in polynomial time. And this is literally just about counting representatives to cover the distributions. That's it. It's just a balls and bins counting, because in each group, you have like at most n items that will take a particular value particular value X, right? And there are at most C different values and S different groups. So you need n to the CS many different representatives to like cover this distribution. But the main thing to remember is that when you have small marginal support and only few distinct kinds of marginals, then you can find the optimal mechanism in polynomial time. But this is for this very special instance where you have finite support marginals and finitely many distinct marginals. We can't really extend this immediately to beyond this instance. Like you can't even cover all like finite support distributions with this method, like directly. Like for example, consider this again a very simple instance where the values take 1 or 2, but they are not identical anymore. They're going to be very asymmetric. Everything is different. There are again 2 to the n many different types of buyers. So you know how to do it in exponential time. We can just do the naive LP way. But can we do better? Is there a polytime solution for this instance? It's not clear. Can we get a polytime approximation scheme for this instance? We don't know. We actually still don't know if for bounded distributions, a polytime approximation scheme exists or not. We don't know that. Okay. So yeah, the main takeaway from this part is that symmetries are very awesome. Like you can get the optimal mechanism in polynomial time as long as you have finite marginal support and like finitely many distinct marginals. But it is not clear how to extend this beyond the symmetric distributions to even bounded distributions. And now I'm going to be talking about what exactly is the challenge in like going beyond symmetric distributions. Why is it so hard? As Michal was asking, why can't we say that like, oh, we have a bounded distribution. Maybe we can find something that is a symmetric distribution which is close by. That is, maybe this is an approximately symmetric distributions, and can't we just like apply the Dust-Clarke-Weinberg result? Like, can't we just do a transformation from a bounded distribution to a closed symmetric distribution? The issue here is like, it is very, very important what we mean by a closed symmetric distribution or like an approximately symmetric distribution. Because just because 2 kinds of distributions are close in some sense does not mean that the revenue is going to be preserved. For example, look at distribution D. The value, the item takes value 100 with probability half and 0 otherwise. And there's a distribution D prime where the item takes value 99 with probability half and 0 otherwise. So these are like similar distributions in some sense. You can also think of this like 100 minus epsilon or something. Like they're quite similar distributions in some sense, but the mechanism that sets price 100, which is optimal for D, gets 0 revenue for D prime, right? Like we also need to take care of like what we mean, like how we handle these closed distributions, because a mechanism which is optimal for D and gets revenue 50 can get 0 revenue for this closed distribution D prime. So for this reason, it is very important what we mean by transforming into a closed distribution and what this metric of closeness is. What do we mean by an approximately symmetric distribution? And that is, I think, yeah.
I think if you use the Prokhorov metric, you do get continuity. If I remember correctly. Sorry, that's a distance between distributions by, say, Prokhorov metric, which corresponds to the weak convergence of distributions. Then there is continuity.
Sorry, I'm not sure I understand what metric you're talking
about. You are asking, I mean, the distance between distributions, there is a natural metric that corresponds to weak convergence of distributions.
I see. Okay.
Okay, it's called the Prokhorov metric. It's called the Prokhorov metric, which tells you that the distance is epsilon. If 1 minus epsilon of the distribution, I mean, you are allowed epsilon the probability to do wild things, and with probability 1 minus epsilon values, you moved values by no more than epsilon. That's what it says.
Yeah, okay, I see.
And that's a Prokhorov metric, and with respect to that, I think you do get continuity of the revenue.
Kind of, yes.
That's no. I mean, it's not difficult. It's not difficult, but that's. Yeah, I think that's the right metric.
It's about getting the right metric and about like also. So, for example, like what you're saying would not work for the additive buyer because it won't be close enough in some sense. I want something close enough.
Sorry, I should say that is known for the additive. I don't know about unit demand. Maybe unit demand has some quirks that. I'm talking about additive. But wait, there is a constant between them, so continuity is continuity for both. No, I take it back. It's okay. It should.
I'm very confused. I'm sorry. I lost you for a bit. I don't understand what you're saying.
Never mind.
Okay.
Go on.
Okay. Yeah. So right, it is important to like understand like what this close means, so that like we will preserve the revenue. And that is the challenge that we like face. And what we say is that you can actually transform any bounded like distribution. Like, so we kind of say that any bounded distribution is actually approximately symmetric in the right notion. And then we use the optimal mechanism for the symmetric distribution that is close, and using the Dess-Clarke-Weinberg result. And then we do another like careful transformation, which is kind of what what we do in a standard way, because it turns out when we look at the optimal mechanism for this symmetric distribution, it is like epsilon truthful for the original distribution. So we do a transformation of the mechanisms by just like discounting prices to make sure that we preserve revenue across all of this, and we get the optimal revenue. And this happens in quasi-polynomial time. Like we can start with any bounded distribution, find a close symmetric distribution which has like finite marginal support and small distinct kinds of marginals. And then we will show that like you can get the almost optimal revenue by tweaking the optimal mechanism for this close symmetric distribution. Okay. So the main takeaway from this part is that symmetric distributions are very fragile. It is not trivial to say that, okay, something is approximately symmetric, so it should get up to approximately optimal revenue. There is some work to be done to like do a careful transformation from going from like any bounded distribution to symmetric distributions so that we can preserve the revenue and get almost optimal revenue. Okay. So yeah. And Now I want to talk about the challenges that we face in going all the way to our general setting of like unbounded distributions. Here again, maybe you might think, okay, maybe we can find a value v after which the probability that you see anything beyond this is so negligible, and why can't we just chop off the distribution? Why do we need to work with unbounded distributions? It's because if you want a 1 minus epsilon approximation to the optimal revenue, we cannot just ignore the high values completely. Like we can't do that. For instance, let's look at this example to get some intuition as to why. We have n identical items, and the value for each item is drawn with a very high probability from uniform 0, 1. Okay, so with a very high probability, you draw it uniformly from the interval 0, 1. And with a very small probability of 1 over n square, it takes this huge value h. So now if we ignore the high values and only focus on the core, the bounded interval part, we can get revenue almost 1, because the max of like n uniform 0, 1 variables are going to be like close to 1. So if you set price close to 1 with high probability, it will sell. But if you only focus on the tail, for example, if you focus on the high valued buyers, they're like quite like huge, we can actually get again a good price for them. If you set price h for all items, like a bundle of price h for all items, then we know that with probability 1 over n square, at least one of them is going to be h. So you get revenue close to like h over n. Okay, so now if these two revenues are comparable, if h is like order n, then we can't get better than a constant fraction by ignoring one or the other. So it is very, very important to handle both of them. And that is like the tricky part. Like, how can we make sure that like we don't lose the revenue from the core and the tail? Okay. And I'm going to call such distributions actually almost bounded distributions. That is, in a almost bounded distribution, the support is a bounded interval except for one high, like very high value h. I don't care about what the value of h is, but it's going to be one high value, and the support is a union of the bounded interval with the high value. I'm going to call all such distributions almost bounded distributions. Okay, and we see that you can get a polytime reduction from solving for 1 minus epsilon approximations for unbounded distributions to just solving for like epsilon approximations for almost bounded distributions. Okay, we give this black box reduction that now tells us that all we have to do is to focus on almost bounded distributions. We can't just ignore the tail completely, but it is enough to capture the whole tail with like one high value. Okay, and a similar reduction was like this was done before by Babayev et al. And they do this for the additive buyer setting. They get an almost reduction to a truly bounded distribution. But as I just said, it is kind of like not possible to get a true reduction to a bounded distribution. So they get an almost reduction to a bounded distribution and then like work with that. Like we give a true black box reduction to almost bounded distributions, and this is true beyond unit demand. Like we can, and this result is true even for like the subadditive buyer valuations. So yeah, so we give a true black box reduction to almost bounded distributions. So now from now onwards, all we have to do is focus on almost bounded distributions, and we think that this will be crucial in extending our results beyond the unit demand setting. Okay. So the main takeaway from this part is that we have a polytime like black box reduction from unbounded distributions to almost bounded distributions. That is, we can't ignore the high values completely, but we can capture them with just one high number. Okay. Cool. And now recall the careful symmetrization I was talking about for like any bounded distribution to get the almost optimal revenue. It turns out that like we can actually prove that for any almost bounded distribution, like so any almost bounded distribution, we show that we can do a careful symmetrization to preserve revenue, and so we get almost optimal revenue in quasi-polynomial time for any almost bounded distribution. So by putting these two things together, we get our main result, which is we get a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time. And we do this in 2 key steps. One is the polytime black box reduction from unbounded distributions to like bounded distributions, almost bounded distributions. And 2 is carefully doing a symmetrization to go from any almost bounded distribution to symmetric distributions and getting almost optimal revenue for it.
Question. This reduction to almost bounded distributions is done good by good, or you have to look at the whole vector of f's to make the reduction? You understand the question? I mean, you can do it for each good. You get an fi and you reduce it to an almost bounded, regardless of what the other f's are. Or you have to look at the joint at the fact at f1 up to fn, and only then you'll know how you replace f1 by, say, f1 prime. Which one of this is true?
That's a good question. I actually think it's can be done good by good, but I might be wrong. I'm blanking out a little bit because like the main thing that we see is needed is like this connection between at what price, like the way we will apply this is to like this connection between at what price we are going to like the maximum probability with which we will sell the bounded part versus like what can we price the high value. So from from whatever I can like remember, I am quite confident that it is done item by item, but there is a small probability that I am wrong.
Okay, but that would require knowing. I mean, you said that you have an oracle that gives you, say, F1, but that gives you the milestone price of F1. But to do the reduction, you need much more than that. No, or I'm wrong?
No, you just
milestone price of F1
for the reduction. All we need is like you have oracle access to like CDF and PDF of values and like the Meyerson price of so the it's not Meyerson price of F1. What I said, like what I want is the Meyerson price of any threshold. Like for F1, I want the Meyerson price that is greater than T. Like if I can only sell my item at price greater than T, what is the max, like what is the optimal price to sell it at? So I want to do queries like that. Like, okay, this is your threshold. Tell me what is the Meyerson price if I can only sell at price greater than T.
Okay, the number of queries, I guess, is bounded or something.
Yeah. The number
is
of queries
fixed or something. It's a function of epsilon, but
yeah.
Okay.
It will be like it can be a function of epsilon, but it's going to be polynomial in n. Yeah.
So Divi, I have a question. So you said before that key step 1, you have all the way to sub-additive valuations, right?
Yeah.
So I guess it's the step 2 that is specialized to unit demand.
Correct.
Do you know anything on step 2 beyond the unit demand? That's the first question. And then the second question, I think I lost you in this. So you said there is a previous result that gives almost reduction to bounded and your result that gives true reduction to almost bounded.
Correct.
So what about true reduction to truly bounded?
Yeah, so the reason why the true reduction to truly bounded is hard or like kind of like not really possible is that you have these examples where you can't ignore the tail completely. Like it just doesn't make sense to like ignore the tail because you will lose constant fraction of the revenue if you ignore the tail. So you have
even if for one good, that's true. That's true. Think about one good where the tail is fatter than 1 over p.
Yeah.
Say the tail is 1 over square root of p. Any bound that you put, you are going to get a finite number, and the revenue is infinite. So you get an infinite gap. Just, I mean, I know it's extreme, but still, it shows you that even for one good, you cannot get bounded.
Yeah, we can't just do we can't just chop it off at like a bounded distribution. Like that's not going to happen. Like
I mean, I'm talking about the maximum.
When you say
like,
bounded,
I am assuming that my revenue
when you say bounded, you mean to trim it to some.
So okay, this is a good question. So what is the difference between a bounded and an almost bounded distribution? Like technically, this almost bounded distribution is bounded at h, right? Like that is true. So what I mean by something that is bounded versus something that is almost bounded is that the bounded interval part is going to be like, it's not going to depend on n. It's going to be this like truly bounded distribution that's like between two constants.
Oh, I see, because for your result, you need h to be significantly higher than n.
I want
and all you do is like shift the whole mass beyond your bound to the h.
So h can be like very big. H can be like order n, like it is going to be like polynomial in n. So but it is still just one point. It's not like I don't need to tell you how the whole tail is. I just need this one point, which is like this huge value that's like somewhere, but everything else is like in this nice bounded interval, which is like there is not it's like it is like a constantly bounded interval, like it doesn't depend on n.
And the last question is about step 2. Do you have any implications for step 2 to additive valuation?
So not a lot of good news is there. I have been working on it for quite a bit. So one issue with just directly, I can tell you what is the barrier in applying step 2 directly in a very like simple sense, is that when I say I want something to be close to a symmetric distribution, I need it to be close enough so that the error is not too much. The error from being not exactly symmetric is not too much. Like I want to make sure like I get 1 minus epsilon approximations, right? I can't, if I do the same thing, if I don't do anything else, if I just look at the same transformation, it will give me like 1 minus n epsilon approximation. Like for additive, it kind of, we really use the fact that it's unit demand to bound the error between like what is like the true distribution and the symmetric distribution that we look at. And
but I think there's for additive, there's a different problem. Even for IID, which is the most symmetric you can have, I don't think you can get a 1 minus epsilon approximation in polynomial time. We can.
That's one of the results. Yeah, we actually do show you can get a 1, but in quasi-polynomial time. It's not going to be polynomial. It's going to be again quasi-polynomial, like so if it's IID, you can get a 1 minus epsilon approximation quasi-polynomial time. Yeah, it's just because now the symmetries are going to be, it's just too symmetric. Like, so what I will, so if we are, let me go back and try to tell you.
By the way, also, Divya, we are close to the end, so feel free to just take everything offline, and if you choose to,
I can tell you more about this thing offline. All I want to say that yes, the second part is like very specific to unit demand, and it's not. It's hard to do it for additive, and we actually have like kind of like a barrier example to say why this particular approach won't work, but yeah, we can talk more about this later. Right. So I am going to very quickly say that like we also look at a different notion of simplicity called like menu complexity. And I don't know how many people are familiar with this, but like a menu is just a collection of all mechanisms, a collection of all outputs of like a mechanism, like all outcomes, like all allocation and price. This can be a menu. And it turns out a menu is like equivalent to a mechanism, giving someone all the options and asking them to choose is same as running a truthful mechanism. And the menu complexity is just the number of distinct outcomes of a mechanism. So we define this new notion of symmetric menu complexity, where we basically say that you can get a more compact menu, like while implicitly agreeing to like something. For example, here, instead of explicitly listing out all different combinations, I can just give this compact menu with an asterisk that said that, okay, you can take any combination of the balls, but like these are the prices for like the different number of balls. So in the interest of time, I'm going to like not define it more generally than this, but like we are basically going to be given a list of options along with the permutation subgroup like sigma. And this is a symmetric menu. It is basically saying that if I give you some option like allocation and price, I'm also giving you implicitly giving the option of choosing anything that is permuted, the permuted allocation at the same price P for all the permutations in this subgroup sigma. Okay, and we see that this is like a very useful notion of like simplicity, and like and we see that our like almost optimal like mechanism from earlier has quasi-polynomial symmetric menu complexity. That is, we can get almost optimal revenue with the menu which has like quasi-polynomial, like almost polynomial symmetric menu complexity. And we also have like analogous results to the computational case here. And yeah, so I think with that, I'm going to like wrap up with a summary. We see that optimal auctions are complex and like can be computationally hard. And our work gives the first sub-exponential mechanism that gets almost optimal revenue for a general class of distributions called unit demand buyers. And we give a true black box reduction from solving for unbounded distributions to just almost bounded distributions. And this holds true even for like subadditive buyers. So for going forward, all we need to focus on is almost bounded distributions. Yeah, and we see that we can exploit symmetries in seemingly very, very asymmetric distributions. And we define a new notion of symmetric menu complex, like new notion of simplicity called symmetric menu complexity. There are like a lot of open questions here. One is extending this to like beyond unit demand, like can we, because we have the reduction to almost bounded distributions, so can we get sub-exponential time approximation schemes for an additive buyer or even like sub-additive buyer? And yeah, like let me know if you have any questions. Thank you.